All right, let's talk about the invisible magic that powers pretty much everything in our modern world, the antenna. Today, we're going on a journey. We're going to see how we went from a single, simple voice to a powerful, focused chorus that can literally reach across the stars. I mean, think about it. We use this stuff constantly. Our Wi-Fi, our phones, the radio in our cars. But have you ever really paused and wondered, how does it actually work? How does an invisible signal just travel through thin air from one spot to another? Well, that's the big question we're going to answer today. And to get that answer, we have to start at the beginning with the most fundamental piece of the entire puzzle. So let's dive into section 1, the basic dipole antenna. You can think of this as the essential Lego brick of all wireless communication. At its core, the idea is just beautifully simple. A dipole antenna is really just two pieces of metal, and its whole job is to be a translator. It takes electricity and turns it into a radio wave, or it catches a radio wave and turns it back into electricity. It's a perfect two-way street for information. And honestly, the best way to wrap your head around this is to think of the dipole as the vocal cords of electronics. You know, just like your vocal cords turn puffs of air into sound, an antenna turns a jolt of electricity into an invisible sound, a radio wave that lets our devices talk to each other. Okay, so we know it acts like vocal cords, but how does it actually create that invisible sound? That brings us right to our next section, how antennas radiate energy, and that incredible journey from a simple current to a traveling wave. The key concept here is something called the radiation field, and the best way to picture this is to imagine dropping a pebble into a perfectly still pond. The antenna is that pebble, and the radio waves, well, they're the ripples that spread out from it. That outward-moving energy is the radiation field. So, how do we make those ripples? Well, it all starts when we zap the antenna with an alternating current. That's just electricity that's flipping back and forth really fast. That moving charge creates this fluctuating electromagnetic field right around the antenna. And then, the amazing part. That field expands outward and actually detaches from the antenna, launching itself into space as a radio wave that just keeps on going. Now, not all antennas are created equal, and to measure just how good one is, we use a term called radiation resistance. And I know what you're thinking. Resistance sounds like a bad thing, right? But here, it's actually a measure of efficiency. It tells you how good the antenna is at turning raw electrical power into radio waves. A higher radiation resistance means a stronger, clearer signal. It's like the difference between a mumble and a crystal clear announcement. And this basic design is incredibly versatile, which brings us to section 3, where we're going to look at the two main flavors it comes in, grounded versus ungrounded. So first up, you've got the ungrounded antenna. It's symmetrical, it's totally self-contained, which makes it perfect for things that are flying through space or the sky, like satellites and airplanes. But then you have the grounded antenna, which has this really clever trick up its sleeve. It actually uses the entire planet Earth as the other half of its antenna. How cool is that? That's why it's asymmetrical, and it's the design you see in those giant AM radio towers or even that little antenna on your car.
Okay, so we've mastered the single voice. But what happens when you need to shout a message across a huge distance? Well, this brings us to section 4, strength in numbers, and how we start building that powerful chorus using antenna arrays.
This is the fundamental problem, right? A single dipole is useful, but its reach is limited. And its signal just kind of spreads out everywhere, which wastes a ton of energy. So what do you do when one voice just isn't loud enough to get the message where you need it to go? The answer is so simple, it's brilliant. You just use more than one. By combining antennas, you create something way more powerful than any single one could ever be on its own. It's all about teamwork. And that's what an antenna array is. It's a whole group of those basic antennas we talked about, all arranged in a very specific pattern and timed perfectly so they work together, in concert. They act like a single, much bigger, much more powerful, and way more focused antenna. It's the definition of teamwork for radio waves.
But it's not just about being louder, it's about being smarter. And that brings us to the really cool part in section 5, where we see exactly how we can focus that signal using something called a broadside array.
So remember those ripples from our single antenna? Well, if you could actually see the energy coming off of it, it would look like a giant, invisible donut. A lot of that energy is wasted going up toward the sky or down to the ground, places you don't need it to go. It's powerful, sure, but it's not focused at all.
Now here's where the magic happens. When you arrange a bunch of these dipoles side by side in a broadside array, their individual donut patterns start to interfere with each other. The waves cancel each other out in most directions, but they add up and become super powerful in one specific direction. And the result? You've taken all that scattered energy and focused it into a single, narrow, powerful beam. You've basically gone from a lantern to a laser pointer. And this brings us right back to our mini idea. This is literally the difference between a single person talking in a big room and an entire chorus singing in perfect harmony. Every voice is aimed in the exact same direction, creating this unified wave of sound that travels so much farther and is heard with perfect clarity. This is the exact principle that lets us talk to probes in deep space and what makes your 5G connection so incredibly fast. So we've gone from a simple piece of metal to a highly directed beam of pure information, all just by understanding the physics of waves and the power of teamwork. It really leaves you with a final thought, doesn't it? If we can learn to so precisely direct an invisible force like radio waves, what other invisible forces are out there that we'll learn to direct next?